So in part one, we saw why the coil might turn, and in part two, we saw that we needed a split ring commutator to allow the current to reverse every 180 degrees. In this part, we're going to have a look at what we can do to make a much better motor than this one with just a simple coil. Now, these bullet points are taken from England again, the same section. And the first thing is a large current. The bigger the current, the bigger the force. So, great. What's not to like about that? And actually, since the force acts on each wire, then if we have twice as many turns, we have twice as much force. So that's all pretty good as well. But it does have one slight snag. How big are we going to end up? So if you want a motor that's going to fit into a Scalextric car, or indeed a real motor car, you can't make it too big. And if you need a large current and you need lots of turns, then it could get pretty big. Now, the third bullet point, more than one coil can be put on the rotor. Now, this is the secret to it becoming self-starting. We saw that when our coil got to this vertical position like this, then the turning effect, we better make our magnet a little bit bigger actually, the turning effect became zero. And so this orientation was useless. The turning effect became zero on account of the fact that our coil was simply being pulled apart. It wasn't actually being made to rotate. It was being pulled this way and this way by the magnetic field. Well, what we can do to get over that problem, we've got a magnetic field going from north to south. What about those two forces are useless? Let's have another coil at a different angle. Okay, let's have another coil at sort of this angle. Now, I'll just draw 3 coils. But actually, in a real motor, you have loads of separate coils at slightly different angles. So there's always a coil that's getting a turning force that can make the rotor spin. So by having lots of separate coils, all at slightly different angles, then we can get a motor that will self-start, and it also, you can see that as the coil turns, the turning moment actually gets less and less. So the horizontal position is actually the best position. So, yep, each coil then experiences a force, so the total turning force on the motor is larger, but the point that they've missed about that is that actually the coils are all at slightly different angles. So sorry, Mr. England, you've kind of missed the point there, that we want all these coils to be at slightly different angles so that we've always got one in the best position. Now, in the next one, instead of a bit of plastic, little blue plastic, let's use some iron. So I'm going to draw the iron in blue, and it's actually going to fill up the whole of this space. You see, magnetic fields love iron, hate air. So by just putting the whole thing with iron, then we get a much stronger magnetic effect. Larger current is good, more turns is good, iron is good. All of these things contribute to making a very strong turning force. And then finally it says curved pole pieces. Well, I just mentioned that magnetic fields love iron, hate air. So why don't we just kind of, it's not getting too messy, I hope. Just make these the shape of the magnet. Just come right out to there. And then you've got a very, very small gap. The gap actually is designed to be tiny, 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 0.5 millimeter. And sometimes, as a result, when an electric drill has started to wear out and the bearings have become a bit worn, it squawks. And the reason it squawks is because the rotor is touching the pole pieces. So all those factors outlined by Mr. England pretty successfully, apart from number 3, contribute to making a DC motor that's really good. And modern ones are, better than ever. So thank you very much to the engineers who've developed these things. So that's the end of part 3. And finally, part 4 next time is we'll have a look at another practical use of the motor effect, and that is we're going to make a loudspeaker.